The first one we're going to work through is the KSP problem. I'm going to look at it from two different perspectives. So lead to iodide, first thing, I was going to say, write the compound, but we have the compound right there. So lead to iodide has a KSP. So let's talk about what SP stands for. What does that mean? Solubility. So what are we asking about that lead to iodine? Solubility? Solubility. What are we trying to figure out about that lead to iodine? See if you can write that. Finish that out. True? Something very important that I want you guys to connect. It may not have anything to do with the problem at all, but a lot of the times it might. In terms of KSP, whenever you see KSP, I want you to think this. What does that mean? The ion ratio. Whenever you see KSP, I need that to flash into your brain. What is our ion to ion ratio? It's what? 1 to 2. Does anybody remember that cheat thing I taught you? Y'all, did I show you how I figured that one out? Y'all, let's just show it just to make sure. If it's a 1 to 2 ratio, you raise each value to the power of itself, which is 1 and 2, and multiply them together. So what is 1 times 1? 1. What is 2 squared? 4, right? And then what you do is you just add the two numbers together. So it would be 4s cubed. Okay? If I did it with 2 and 3, it would be 108. If I did it with 1 and 3, it would be 27s to the 4th. Okay, so I just want to throw that at you. So we know that a 1 to 2 is what? 4s cubed. We may not even use that, but I just want to throw it at you. Okay? That's what I need to see flashing. And then it says, what is the molar solubility? What is that short or long for? S. We are solving for S. Well, now does that little cheat method help me out? Absolutely. The first thing I want you to do is write the K for this reaction. Write the K for it. You agree that would be true? All right. I'm going to do this the short way, and then I'm going to do it the long way to prove why the short way works. Okay? So, we know that the KSP value is what? Okay? So, since it's a 1 to 2 ion-to-ion ratio, what can we set KSP equal to? You agree that would be true? But why is it 4s cubed? It's a 1 to 2 ratio. Now, I do need some help with the calculator part of this. How would you do this in the calculator? If you don't know how to do a cube root, what else could you do? Raise it to the what? 1/3 power. You with me? Okay. Because it's hard to do a fifth root, right? Just raise it to the 1/5 power. All right. Actually, there is an answer. I don't have the answer key. No, we have that because it's tethered to it. Yep, that's it. Okay. Yeah, just no, the top one. Just that one. Thank you. Okay. All right. The answer is choice 3. So it's 1.5 times 10 to the negative third. And I'm telling you now, this is where you're going to get messed up. What's the unit on this thing? Molar. Why? What are we calculating specifically? The molar, go ahead, solubility. Yes, they teach this. This is what they teach. Now, I told you I was going to show you the short way, and I'm going to show you the long way to know where this came from. Okay? All right, so has everybody got this? Yes. Yep. Matter of fact, as I was teaching that in second period, I was like, there's got to be a way for them to remember, and I started thinking, and it worked every single time. All right, so let me show you where this actually all came from, the long version. This is why you're here, right, Fuller? This is why I'm showing you. Okay, so I'm going to take that little short version to show you where all that stuff condensed down into. So it was P, B, I2. Is that right? Okay, I thought it was, for some reason I was thinking chloride. 2I minus. In most solid precipitate reactions, when we mix it with water, first of all, this is a solid, right? What do we know about solids? Get rid of them. Can you do this in all rice tables? No. Only ones that contain solids, right? Okay. So initially, what do we have of our ion if we're mixing it with water? Before any reaction occurs, how much is there? Nothing, right? When would you have an I value for a KSP? If you're mixing it with a common ion, right? If I take lead 2 iodide and I mix it with some lead nitrate, what would be in common with that lead? Lead, you have some lead already floating around, right? Or if I mix the lead iodide with potassium iodide, what would you have floating around already? The iodide ion, right? Okay. Now, in the C row, what always matters? Coefficients, right? Now, are we going to make ions or lose ions when we dissolve a solid? Make. So is that positive or negative? Positive S, positive 2S, right? Why is it 2S? That's the coefficients, right? So, we just bring the math down, right? Now, what is 0 plus S? It's S, right? What is 0 plus 2S? You with me on that? All right, so here's the key. Here's the kicker to all of this. I know I'm cramming this into the side. If we have no EF, what does EF stand for? The concentration at equilibrium, right? If we have no EF, which do we have any EF values? You take EX and do what with it? Plug it into what? To K. Can I erase all this over here to the left? That's not the right button. What was K again? You've already written K. Alright, so what I told you to do was take the EF row and plug it into K. What was the value that I would plug in for the lead iodide concentration? Do you agree that's true? All I did was take this number and plug it right in. What do I plug in for I2 for I minus? 2S, and what do I do with it? All I did was take this and plug it right in. You guys tell me, what is S times 2S squared? I reduced all of that rice table right into that. Think about how much time you've just saved. Is that one of those mind-blowing kind of things? Go ahead. All that is memorizing. So what do you have to know? And I'll come right back to it, I promise. What's the whole thing that you need to connect? You see KSP, think ion to ion. When you think ion to ion, know what the ratio is, and you know what your S formula is. And you've skipped the entire rice table. You with me? Hint, hint, wink, wink. You may want to listen to this. What if the question added a part to it? And I'm going to rate, I need to keep this. Part B. So, hint, hint, wink, wink. What if it asks about a specific ion's concentration at equilibrium? So if we go back to our rice table, to know what part? Do you agree I'm wanting to know that thing right there? How do I find EF? Do I have S? What do you do with it? Plug it in and multiply by 2. Okay, so here's the deal. What we tried to determine, what was the question in green circle asking for specifically? Molar solubility, which is S specifically. And then part B says, what is the iodine's concentration? You would double that value. Because think about it either way. If S is 1 to the 1.5 times the negative third, if you plug in S, what do you do with it? Right here, it tells us to double it. So instead of having to do the Rice table, can I show you the easy way? If it asks you for the iodine ion concentration, if you tried to plug S in right there, what would you have to do? Double it. Pay attention to the what? The coefficients. Don't square it. Double it. Because if you think about it in Rice table, what would you do? You double it. I'm telling you, hint, hint, wink, wink. Pay attention to the coefficients at a specific ion concentration. I'm going to completely change the problem but use the same numbers. What if it's not PbI2 anymore? Alright, let's just pretend. Alright, let's just, I know the numbers will be way off. But let's say we used, change it from green. Let's say we used Ni2O3. You agree that would be true? You with me on that? Alright, first of all, what's your ion to ion ratio? Alright, it's a 2 to 3 ratio. What's the 2 to 3 ratio S formula? 108 S to the 5th. I know that would be complicated math. Let's just pretend that this is the KSP and we did 108 S to the 5th and we got that number at the bottom. I know that that's not the right answer. But what if it came back and no longer said, what is the iodine concentration? What if it wanted the oxygen concentration? What would you do to it? You triple it. No, you're fine. You triple it. So what do you pay attention to? Pay attention to these coefficients. So, if they ask you for the molar solubility, which is S, are you good with this answer? But what if they ask you about a specific ion? Pay attention to the coefficients. Go ahead. Do it the opposite way. Divide it by 108 first and then fifth rule. That would give you S. That's all you have to do. That's all you have to do. It's like mole to mole, but it's not mole to mole. It's really ion to ion. Alright. So that's the first problem. Again, I know I totally kind of changed pace on you, but there's a reason I showed you that. Okay? That's the answer to that one. Alright, question 16. Calcium phosphate is only slightly soluble. In fact, its common ingredient in phosphate rock is a major source of phosphate fertilizer. If the molar solubility is, right, what did they just tell me right here? They just told me, oh, that's not right. Okay, they just told me. Steve, you want to join us? They just told us S, right? Is 207. What is the value of the KSP? So, the first thing I want you to do, without even doing a balanced equation, see if you can write the KSP for it. Without even the balanced equation. Think you can do it? Seth, you get all those sheets. That's what we're working on, those sheets. Because think about it, if you take the subscripts and you take the thing and separate it, the subscripts turn into coefficients. Does that make sense? Okay. Alright, so now, remember when I told you, when you see KSP, what do you have to think? Ion to ion. In this case, what is our ion to ion? What is it? No, it's actually 3 to 2. And what is the S formula for 3 to 2? 108 S to the 5th. So, do you agree that we're solving for KSP? You with me? Okay. And then it says 108 S to the 5th. So what do? Take this number. Oh, yeah, we're not saying. Plug it in, it's off. How easy is that? That's it. You're done. Super simple. Yeah. Okay. It's easy, right? Raise it to the 5th and then multiply it times 108. And the answer is choice 3. Can I show you their long version? What? Did you didn't get the answer? Well, somebody plug it in just to make sure that 3 is right. Whoa, that doesn't make any sense, does it? Wow, that is a bad typo. It should be 10. Yeah. How would you? Is that real? Here, Miss Folds, figure this out. So it is the third one, right? Okay. Let me show you the Rice table version of this, okay? And this is if you learn the cheat method, this is how they would want to teach you. You would just, yeah, that doesn't make any sense, right? If you did the Rice table, remember how if we have the Rice table, it was 3s cubed, and then 2s squared. All they did was plug the s in twice. So if you memorize the 108 s to the 5th, guess what? You've eliminated all that other stuff. That's why I teach it the shortcut method. You like it a lot easier, right? Only for KSP, though. Go ahead. Number 3. It's actually 3 times 10 to the negative 32nd. Yeah, that was a typo. Okay. Alright, the KSP of silver chromate is 9 times 10 to the negative 12. What would be the solubility of this compound that was already in a 0.1 molar potassium chromate? Uh-oh. What are we mixing this solution with? Potassium chromate. So we're no longer mixing it with water, are we? As soon as you're not mixing it with water, that little cheat method goes out the window. Okay? So what is this when they say potassium? It is a common ion. Okay? So we now know that potassium chromate is the common ion. So I do want you to do this one because it's going to make everything make a lot more sense. So let's go back and let's do a Rice table for this. Wrong button, clear. I'm glad I'm tall sometimes. What? I feel like this board is longer than. No, but I feel like I got to go way over here, and I don't ever have to do that in mine. Yeah. You can't reach it? Yeah. I don't have a problem with that normally. Okay. What was the? Again, it was silver chromate, right? All right. So Ag2CrO4 in equilibrium with 2Ag plus CrO4 2 minus. Now, what do we know about the silver chromate? What can we do with it? We can eliminate it, right? It's no use of us. Okay? Why are we eliminating it? It's a solid. Now, here's the problem. When we mix this thing with water, do we have any of these other ions floating around? No. But what are we mixing it with this time? We're actually mixing it with K2Cr. Wow, I just butchered that whole thing. Let's try that again. K2. Did it again. K2CrO4. What was the concentration? Alright, so we're mixing it with 0.1 molar K2CrO4. Now, which ion is in common? So what that tells me is that initially I had 1 molar. Now, let me throw something at you because this is important. Let's pretend for just a second that the K was the common ion. Let's just pretend. What would the concentration be of the potassium ion? 0.2. Why? Because this affects that. Be very careful with those. You do have to pay attention to that ion-to-ion ratio, okay? But in this case, we don't have to worry about it. Now, how much of the silver is present? Nothing. You with me? Okay. In the C row, what still matters? Plus 2s plus S, right? Bring it down. So we have 2s, 0.1 plus s. Why don't I keep writing a 5? That's not right. Everybody okay with that? Alright. Do we have any EF values? And I just told you this 2 slides ago. When you have no EF, when you have no EF, what do we do with this thing? Plug it into K. So now let's write our K. KSP is equal to Ag plus squared CrO4 to minus to the first. So I have 2s squared and then 0.1 plus s. Now, second period we've gotten this far. Sixth period we haven't. So this is something you're fixing to see that's new. What's the value of KSP? Did I tell you? 9 times 10 to the... That's not right. Let's change this. 9.0 times 10 to the negative 12. Ethan, all those sheets are there on the far right if you want. Now, second period. You've seen this. I've got to deal with that 0.1 plus s. One more I. Negligible. So, the S is so small, that if I add it back to 0.1, would it change 0.1? Remember, we're talking about KSP to the negative 12. Even if this was S and I plugged it in, would you ever see a change to 0.1? So here's the deal. When it's with a common ion, get rid of the S variable attached to the common ion. Y'all haven't seen this yet. Y'all see this tomorrow. When you're seeing it, you're foreshadowing. Okay? Guess what? You get to sit there and say, I get this when everybody else is up tomorrow. One more time. When it is with the common ion, eliminate the S value. Guess what happens to our math? It gets a lot easier. It does, but it's so small it's not going to have any effect. What's the first thing mathematically we would do to solve for S? I guess we could keep it in brackets, make it a little simpler. What's the first thing we got to do? Divide by 0.1. So the first thing we do is divide by 0.1. Then what would be this? I would leave everything separate and do it as is. I would divide by 0.1. You can. Then I'd divide by 2, and then I'd take the square root. I would do it in steps just like that, just to reassure that everything's good. Does that make sense? So I would divide by 0.1, divide by 2, then take the square root of it. And that's going to give me S. So one more time. Take 9 times 10 to the negative 12th, divide by 0.1. Does that move it to the right or the left? Is that to the 13th or 11th? Okay, that moves it one place to the right. That's right. So the 11th. Then half it, which makes it 4.5 to the negative 12th, right? And then square root of negative 11th. Yeah, I can't figure that one out. The square root of 4.5. It's like 2.3, right? The square root. Is it? That's true. Okay, what is it? Now, we just solved for S, right? So what is S's units? Mole. So what was this one? Why was this one different? Common ion. That was why that one was a little different. Common ion. Yep. Because the question is, what would be the solubility? They're going to say molar solubility. So that's going to give you the clue of solving for this, right? So that's what's going to give us that value. Now, let me ask you something. I'm going to go back, and this is going to tie it back into the very first question. So we found out that S was which value? It's not up there? Did y'all do something wrong with the calculator? It says choice number 4. I know that we're right. There's no way that we're wrong. So what is it again? Times 10 to the what? Maybe that's just a typo. Maybe that should be 6. Alright, so here's my question. We found S, right? My question to you is, what would you do? Why would you double it? Because that right there tells me there are 2 silver ions, right? So take this concentration and double it to whatever that would be. Sounds right. Okay. What would the concentration of the chromate ion be? It would be equivalent to S, right? Because it's got a coefficient or an exponent of 1, or a coefficient. Okay. All right. So let's see. This is something that we skipped in class, and I'm going to skip it. I'm not going to test you on this, but I just want to show you this just because. Will a precipitate of barium sulfate form when 10 milliliters of 0.001 molar barium nitrate are mixed with 20 milliliters of a 0.0002 molar of sodium nitrate? The KSP in barium sulfate is that value. Prove your answer by reporting your calculated Q value. Essentially what you would have to do is solve for Q using these values. It's a difficult process, that's why I'm not spending time on it. It's kind of one of those that they ask you about, will a precipitate form? Congratulations, you got us. I'm moving on to the next question. I can't spend time on this, but it's easy, but it takes about a day's worth of lecture. And I may do it after spring break just so you can see it, so you know what it is, but it will not be tested on our channel. Okay? You got a question? You would have to write a rice table, and here's the problem. you're taking this solution, right, and you're mixing it with this solution. Well, the problem is you have to have enough barium ions from this and enough. Sorry, hold. You have to have enough barium ions from the barium nitrate, and you have to have enough. That doesn't make any sense, does it? There's no sulfate. This would have to be sulfate. Do you see what I'm saying? All right. So you have to have the right ions present to make it happen. But barium nitrate. So you have to have enough of the barium and enough of the sulfate that when they get mixed, they would form. Okay. Exactly. So, but if you look at the formula, there's no sulfate anywhere in either one of those two. And up here it says, will a precipitate of barium sulfate form? But the problem is, when you mix two things, you have to deal with the volume additives. So you have to calculate a new concentration. And it's just, it's very intuitive in terms of steps. But we'll go through that way later. Skip that. So separate a solution containing barium. Slowly add a mixture. Yeah, that's one of those other things we'll have to take time and do it later. What about that increased solubility salts forming complex ion? Definitely skipping the complex ions. Okay, that's the end of that one. We're going to move to another one. Let me see your force change real quick. I want to go. All right, I want to go to the one that's darker looking. It says KSP, solubility, equilibrium, multiple choice. I want to go to that one. Whatever you feel like. Okay. All right. The solubility of CIU is 2 times 10 to the negative 6. Now, as soon as they tell you the solubility is, what did they just tell you? They told you S. What is the solubility product constant, KSP, for CUI? Now, and I've told you, when you see KSP, what do you have to think? Ion to ion, right? What is our ion to ion for this one? It's 1 to 1, which is what? All right. Write your KSP, which is Cu plus, I minus, right? Remember, always write your K value. That you could earn a point simply by writing what I just wrote. That could give you 1 point. Okay? And so we know that KSP for a 1-to-1 is what? S squared. So what do? We take 2 times 10 to the negative 6, and what do we do with it? Square it, which is what? 4 times 10 to the negative 12. Is that right? Sounds right. You square both. You got to remember, tomorrow is multiple choice, so that's all you'd have to do. No, it'll work. It'll work through it. Write the K value and so forth. But if it's a Rice table, show it. All right, number 2. Guys, hint, hint, wink, wink. Catch this. I can't tell you how important that one word is. Y'all want a tip for being here? You want a bonus point? That means they got to watch it. I should. If solution. free test answer. Balls. So if I have a saturated solution that has a lead iodine in it, and I want to know the concentration of a lead iodine if the solution is allowed to evaporate from 100, that's fro, not that's from, not from, from 100 milliliters to 50 milliliters. So the question is, what is the concentration of this ion? The question is, I can't remember if you're going to know the answer by the time I'm finished with it, but so the answer is, yeah. All right, so let's get back to this. What period? I'll be in here, and then first period I go, no, second period I go to this amount. We don't have first amount. Here we go. So in a saturated solution, again, what did we just say about this? At equilibrium, which means the rate of the forward equals the rate of the reverse, so the concentrations remain what? So concentrations are constant. Okay? The solution of zinc hydroxide at 25 degrees Celsius, the value of OH minus is 2 times 10 to the negative 6. What is the value of the solubility product constant for zinc hydroxide? This is a good question. So, do you agree that our KSP, we're solving for KSP, right? Okay, is going to be Zn2 plus OH minus squared. You agree that's true? Okay, and then it tells you that our hydroxide ion concentration is what? Do you agree that's true? So they tell you specifically hydroxide is 2 to the negative 6. What are we missing? We know we're solving for KSP. That's our question. We're missing zinc 2 plus. What is the concentration of zinc? Why is it half? Very good. It's this ion to ion ratio thing again. A lot of people want to plug in the same number. It's not the same. It's only the same when it's the same ratio. So what is the ratio exactly from hydroxide to zinc? It's half. So it's 1 times 10 to the negative 6. You have the you half that value. No. Because this is technically the concentration. So you half that value. You with me? You take half the concentration. So 2 times 10 to the negative 6 squared is what? 4 to the negative 12th? 4 to the negative 12th times 1. Is that 4 to the negative 18? Right or wrong? Oh, wow. I was right. Hey. It makes me happy when I get those numbers right. But that makes sense? Alright, so the whole key to this problem, why did I show you this problem? You have to half the concentration of the zinc ion. Okay? Alright, very good. Alright, let's look at this one. Consider the following systems in equilibrium and the stresses applied to them. Which of the following equilibrium systems would shift so that the products were favored? Second period, I have graded y'all's Le Chatelier thing, the one that were actually essay questions. Y'all did terrible on those because you did not answer the question. We're going to go over those tomorrow. It was the words, and it said, explain and predict the change of K and the moles of CO in the first one. And nobody, they just put shifts this way and shifts that way. I mean, I know what the question says. I've got a key to it. All right. So, let's look at one. Number 1, if I add Cl2, so how do we shift from an addition? All right, so we're going to add here, so we're going to go this way. So what happens? Our product's favored in that one. We're good there. Remove COCl2. We're taking that away, so how do we shift? Toward, so what does that mean? Products are favored. So automatically that knocks A, B, and the rest of them are still good. And then remove PCl3. So I take away this way, and what happens? Shift where? Towards the reactants, right? So that knocks out D and E, so it has to be C. See how easy that was? Okay. Right? Which of the following is the best statement of Le Chatelier's principle? A system in equilibrium will always remain in equilibrium. No. A system in equilibrium will not be affected by a change in concentration. Definitely not. A system in equilibrium will respond to a change by shifting in the direction that reduces the change and restores equilibrium. Ding, 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 we got a winner. Okay? That's definitely going to be it. So 3 is the right answer there. Because the one we just did was 2 of them. It was C. Okay? Of the answer to that? I mean, that's pretty much the answer. That is the best statement. But it will be affected. Yeah, if you add it, it shifts. All right, I'm going to go ahead and tell you, you better know these because these are going to get you on the multiple choice if you don't know. If you know one, you know them all. This is the geek factor. Which of the following must be true for reaction to proceed spontaneously? That tells you everything you need to know. So as soon as it says that, when we write this, G, when it's spontaneous, is what? E is, and K is. You know one, you know them all. Let me tell you where it's going to get you. It's going to actually give you some values. And you're thinking, oh my gosh, I got to do something with this value. If K's exponent is positive, is that greater or less than 1? If the exponent is positive, it's greater than 1. So what does that tell you everything else you need to know? If you know one, you know them all. Focus on that. So what is the answer to this one? There's only one possible. It's got to be C. Why? That's the only one that's G is less than 0, which what's another way to say G is less than 0? It's a negative number. Okay? I'm telling you, there's a lot of those on there. All right, which of the following is the best definition of chemical equilibrium? What? There are equal amounts of products and reactants? This is definitely not true. The forward and reverse reaction rates have stopped. Nope. What kind of reaction would that be? Completion. I'm talking about completion, but equilibrium. The product concentrations are larger than reactant concentrations. It's possible, but is that a good definition of equilibrium? No. Just like that E is not a good one. So it's obviously A, right? Because the key here is the rates are equal and constant. The rates, not concentrations, the rate. Okay? Alright, last one. Number 8. The molar solubility of water of Ag2CrO4, the KSP is. So when you see KSP, what's the first thing you need to think? What is it? Ion to ion, right? What is our ion to ion for Ag2CrO4? Alright, what is your S value for 2 to 1? Did I just break this pen? Oh, gosh, seriously? No way. Seriously? I dropped it and it broke? No way. Alright, well, let's pause this video and let's get a different pen up here. That's crazy. Okay, what is what is your S value? 4S cubed, right? Okay, so what is the molar solubility? What do you notice that you don't have to do? You don't have to do, well, you do have to do a little bit of math, right? What's obviously not going to be your answer choices and why? Why? It's not divided by 4 at all. What about B? What do we know about this thing? Got to have a cubed root, right? The B and C are automatically out. Now we've got it down to 4 and 2. What is 8 divided by 4? Got to be E. You with me? That's easy enough, right? Okay. Process. Go ahead, finish. Yeah, that's what I mean by that. It does, but it's easy math. Stuff you can do in your head. Okay? All right. Okay? All right, so 1985, here's some free response. At 25 degrees, the solubility product constant, KSP, again, I'm just throwing these at you. We may not even need it. When you see KSP, what do you think? Ion to ion? Okay? The KSP for strontium sulfate is, all right, so what's our ion to ion? 1 to 1, which is what S value? S squared. Yay. Got some good stuff there. Is 7.67 second. The solubility product constant for strontium fluoride. Ooh, notice what they just did. Notice what they just did. They went from strontium what? Sulfate to strontium. Why in the heck would they just change compounds? And notice what they did. They didn't give you the KSP. What did they give you? They gave you the solubility product, which is, hold on. No, okay, no, they gave you KSP as well. It says solubility product constant. Okay, so this is also KSP. So they gave you KSP for two different solids, right? Now, go ahead. Yes, very good. So if we wrote the KSP for this, it would be SR2 plus. Very good for catching that. SO4 2 negative. Now, down here, SRF2. What's your ion to ion for that? 1 to 2. What's your S value? Now, I'm going to throw this at you. We may not even need this. As a matter of fact, I caught this in a multiple choice question, and I emailed some of our head AP people, and they said, yes, it's a bad question. Don't give it to them. Can you compare the solubility of solids using their KSP values? Yes. Remember what we said. The lower the KSP, the less soluble. So let's write that down. Now, there is one major important fact about that statement that makes this doable. What has to be the same to compare? Very good. Must be the same ion to ion. So the only time that you can compare the solubilities of solids using their KSP is if they're the what? Same ion to ion ratio. That's it. It's the only time you can compare them. So if we go back to our problem, everybody good on this? Say no if you're not. Or not, whatever you want to say. Okay, alright. So now that we know this, can we use their KSPs to determine which one's less soluble? Can we? They're not the same ion-to-ion ratio, right? One is 1 to 1, one is 1 to 2, so you can't compare them. So here's the question. What is the molar solubility? What are they asking us to solve for right there? They're asking us to solve for S for SrSO4. In what? This is good news. In pure water. So we don't have to worry about that coefficient or the common ion thing, right? Can you use your cheat method doing this. That's why this thing is so important. So we're going to say that the KSP is equal to SR2 plus SO4 2 minus. And what was the KSP value? You guys have it right there in front of you for strontium sulfate. Be careful. 10 to the negative 7th. That was a bad 7. And we know that it is going to be S squared, right? Do you agree this is a super simple problem? So somebody's going to read that for me. Now, we just solved for S. What's your unit? You're good. Now, I'm going to look at something real quick. Pull this up. This was my key. Notice what you got. Notice was the average up here. I know that's really, really hard to see, so let's blow it up a little bit. Let's, I can't zoom in. Can y'all see the average up here? 2.87. 2.87 point average on this question back in 1985. Notice what we did. You get 1 point for writing the values, don't you? You with me? You got 1 point for writing your K. That's why I stressed you, always write your K expression. And use S squared. Now, do you have to show all of this extra math? It makes it look prettier. It makes you like you know what you're doing. I would at least, you don't have to show the square root of KSP, but I would at least show this part right here. And then you get 1 point. So you get 2 points for that. You guys are already halfway to the average. That's awesome. Okay? All right, so let's go back to this. So part B. What is the molar solubility of SF2 in pure water? Well, if we know our cheat method, what do? I'm actually going to add right here. So KSP is equal to SR2 plus F minus squared. What was the KSP value for this one? 7.9 times 10 to the negative 10th. Alright, what's your ion-to-ion ratio? 2 to 1. So what's your S value? Run your math. Do y'all like that cheat method? It's too easy to mess up. I hope it's too easy to mess up. So if they ask you for molar solubility, you're solving for S. If it's in pure water, are you good to go? But when that common ion pops up, we got to know what to do with it. What do you do with the common ion? Remember, you add the concentration of that ion in for S and cancel out the S. Does that make sense? Okay. Anybody got this real quick? 5 point what? Times 10 to the negative 4th. And molar. 5.8 times 10 to the negative 4th molar. Again, I'm going to just show you my key that I have worked out because I'll work it out how you guys would. Notice what this says, and I didn't even notice this. During 1985, if no units were given, they took a point away. Right? That hurts. Now, they don't do that anymore, but see how important units are? Notice what you get. That is not exactly what we got. 1 point for connecting these two things, writing your KSP, and the 4S cube, and then actually solving for it. Guys, you're already past the national average, and we're only 2 questions in. That's pretty good. That's a pretty good sign. All right, that's a pretty good sign. All right. C. An aqueous solution of strontium nitrate is added slowly to a 1 liter of a well-stirred solution containing 0.02 moles of fluoride ion and 0.1 moles of the sulfate ion. You may assume that added SrNO3 does not materially affect the total volume. That's good news because we don't want to have to deal with volume changes. That'll change concentrations, right? Which salt precipitates first? That is something I have not taught you guys yet. see why the points were low on this one? But at least you got 4 of them. So here's what you got to do. The first thing you have to do, let me pull this up. So it told you that the first one is strontium sulfate. Okay? So what they're trying to get you to do is solve for S for both of them. Do we solve S for both of them? Okay. And then what you have to do is you have to compare the S values. Did we compare? Okay. This one is greater. So see, it's been so long since I've looked at this that it kind of confuses me too. How about we just skip that set of confusing it in ourselves? Is that okay? Let's skip that without so we don't confuse ourselves. Alright, so 1990. The solubility of iron 2 hydroxide is, now when they say the solubility, what did they just give you? Kind of. Grams per liter. That's a problem for us, isn't it? We'll talk about that in a second. A, write a balanced equation for the solubility curve. Please do that. Please be able to do that. I was told by Alex, he said, please let us do this because I don't know if I can do this. Write the balanced equation for the solubility equilibrium. You would have to know the molar mass of FeOH. You just look it up on your phone. Do molar mass of FeOH2. Hold on, I got my iPad right here. Let me talk to Google. Okay. 55.85. Okay. Alright, so we've got solubility of iron 3 hydroxide, that's the mass of the generic. There's the balanced equation should be FeOH2 in equilibrium with Fe2 plus 2OH minus. You okay with this? That's what that you would have gotten from that. B, write the expression for the solubility product constant, which is KSP, right? So KSP is equal to what? You agree that's an easy 2 points? Okay. And then it's going to get into C, and you're like, oh my gosh, what is this thing talking about? Calculate the pH of a saturated solution. Oh, and calculate its value. I was thinking that's a little easier than I thought it was going to be. Alright, what's the problem with what they gave us versus what we have here? It's in grams. Now, we know if we need KSP, if we have S, can we use our cheat shortcut method? Now, what is our ion-to-ion ratio? It's 1 to 2, so what's our S formula? 4S cubed. So if I need my KSP, I can do 4S cubed. But again, the problem is, here's what you're going to want to do. You're going to want to take that number and plug it right in as S. But we can't do that because it's in grams per liter. So let me go over here. So we have 0.00143, right? All I did was just get it out of exponential notation. Grams per liter. How do I get rid of this? How do I get it to molarity? What's the only unit I need to change? Okay? I need to get grams into moles. How many times have y'all done that? A lot. So somebody do that for me. Do 0.00143 divided by 89.86. Okay, I'm sorry, Charles. Tell Google that. 1/100th, I don't think it's going to make a big difference. What'd you get from concentration? So, does it make it a little bit more challenging? You even say you were going to mess up? You're going to read through that problem so fast, you're going to miss the unit. You're not going to catch that unit. That's the problem. You read these things a little too quickly. So now we take this, and we plug it into KSP is equal to 4S cubed. So take this number plug it in right there. Seth, can you cube that and then multiply it times 4 for me? .6 times 10 to the negative 14. Does this number have a unit? Yes or no? What did you solve for? You solve for k. It has no unit. Okay, so do we know our S value for our compound? What was our compound? Do you agree that this is our S value? So what if I propose the question? Why would you double your S value? Because the coefficient. So Seth, do that for me, please. This is what, 3 times 10 to the negative 5th? Is it 3 times 10 to the negative 5th? That number double? Yeah, that's right. Alright, so we now know that OH minus is equal to 3 times 10 to the negative 5th. Do you agree with that? Right, what is our next question? Yep. We haven't learned anything about that, have we? Alright, what does pH stand for? It's the acidity scale, right? It's the acid to base. I'm going to teach you this real fast. We'll learn this after spring break. What does our pH scale go to? From 0 to 14, right? What's neutral? Never seen this before? You haven't? We'll get there. So, the question is specifically, I need the pOH. Excuse me, I need the pH. What's the problem with the solution they gave us? Which one of these did they give us? pH stands for hydrogen ion. pOH stands for the hydroxide ion, right? What does P stand for? It stands for the negative log. You're all getting some foreshadowing stuff, okay? So if I have the P, if I want the pOH, I want the negative log of the hydroxide ion concentration. Do I have that number? Do I have that number? Yeah, what is that? What was that number? Yep. Was it to the negative 5th? Oh, yeah, it is. Alright, Seth, do that number for me. Do negative log, or take, however you have to do it in the calculator, of 3 times 10 to the negative 5th. Tell me what you get. You okay with this? So this just gave me the pOH, right? But what did the question want again? pH. How do I get from pOH to pH? Well, what is my pH? What? You guys are smart enough to know this part, though. Is that acidic or basic? Basic. Well, what ion did you have in solution? What is hydroxide? It's a base. Does that make sense? We'll get there. It's easy. You just got to know those formulas. So again, the two formulas that you did not know was this one and this one. Everything else is plug and chug. Okay. All right. I know that was way off task, but we're going to skip that one about the precipitate forming. Let me look at the key and let's see if we can get to something. All right, this is 1994. In a saturated solution, what alarm should be going off? Yep, but what does saturated tell me? It is at equilibrium again, so that's the key right there. So as soon as you see this, we need to say at equilibrium. The good news is I already gave us our balanced equation, and I'm just going to throw this solution of MgF2 at 18 degrees Celsius. The concentration of Mg is 1.21 times 10 to the negative third molar. Now, do you agree that they just gave us this concentration? I'm just going to go ahead and ask. What if first question is, what is the concentration of the fluoride ion? Why would you double it? The coefficient. So what is that? 2.42 times 10 to the negative third? May not even need it, but it's there. The equilibrium is represented by the equation above. Write the expression for KSP and calculate its value. See if you can do it. Write your KSP and plug it in and see if you can do that. I'm going to pause the video while y'all work on that for just 1 second. Okay, so like I said, the first thing that's important, number one, is you get this right. And of course, we could have done the 4s cubed value, okay, because we could have taken it, even though it did say it was for the magnesium ion, the key there is the subscript for it, or the coefficient, was 1. So you can plug it in and solve for 4s cubed and blah, 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 blah. And so this would have been your KSP value. So, well, you could have done it that way. If you know your values, just plug them in. Because here's kind of the way I would have done it. I know that this one was, let me change colors. I know that this one was 1.21 times 10 to the negative third. I know this one was 2.42 times 10 to the negative third. And so I would have just squared that one. And so you come up with the same answer. Okay? Or you can do the 4s cubed thing. Okay? Alright, so here's the reason I want to do this one, and we'll go. Wrong button. Let's get back over here. Let's go to this. So, calculate the equilibrium concentration of Mg2 plus in a 1 liter saturated MgF2 solution at 18 degrees in which 0.1 mole of solid Kf has been added, and then Kf dissolves completely. Assume the volume change is negligible. So what have we just entered into? What was that thing we talked about earlier? Very good. We've now got a common ion in solution. With me? So we've got to take care of that. So I'm going to write this. So we've got R, I, alright, I forgot the C, EX. Now, it said we want the concentration of the magnesium ion at equilibrium, right? Now, first of all, help me out. What's the solid again that we're dealing with? Not Kf, but MgF2, is that right? Alright, so we've got Mg2 plus 2F minus. Now, which one is the common ion when they add? So remember, they're adding. What was the concentration of this NaF? What was the concentration? Did they add NaF or what did they add? Kf. Wow, okay, my bad. So they added Kf. What was the concentration? 0.01. Okay, just 0.1. Okay, so 0.1 molar Kf. So the question they're wanting to know is this value, right? The magnesium ion. Get rid of that. Now, so what is our initial concentration of the magnesium ion? 0, because there's nothing present, right? But what is the fluoride ion concentration initially? Okay, 0.1. So we've got plus S plus 2S. So we've got S and 0.1 plus 2S. What do we know? It's negligible, right? Yep. I'm going to erase all this over here and use this space. So if I need an EF value, I plug this back into K, right? So KSP is S times 0.1 squared. With me? Now, what's the value of the KSP of MgF2? We just saw for it. 7 point something. Times 10 to the negative what? How easy is that math? 0.1 squared is 0.001, right? Jeez, all right, 0.01 divided by this is 7.09 times 10 to the negative 8. Is that true? It's moving at 2 places? No, you're right, it is moving at 2 places. So it's going to be, so S is going to be 7.09 times 10 to the negative 7. Yeah, because 0.01 moves at 2 places, so that's right. So now, what is my sulfate or my magnesium concentration? That makes sense? It would be molar, yes, very good, thank you. Because what's the question? What is the concentration? Yes, why? You trying to be racist? Negligible. Yes, because any. All right, Charles, that's actually a great point. If I take. All right, by the way, here is the answer. Oh, that's not the answer. If I take. All right, here's the answer. So if I take 0.1 plus 2s, and I want to know what that is equal to. You with me? 0.1 plus 2s times 7.09 times 10 to the negative 7. Is this number going to be so small that when you add it to 0.1, is it going to change that 0.1 hardly at all? Because that number is so small. So that's why you can cancel it, because it's negligible, which means it's not going to affect your answer. So if you'll notice what I did here, I have Mg2 plus, I have the 0.1 because I left the S out because it was negligible. Okay? Which gave me that answer. Okay. Any questions? Yes? It's there and it's there. So when I did it right here, because everything goes, remember, so when we wrote our KSP, everything stays squared because you plug into the KSP and the KSP tells you to square. You square the 0.1 as well. Alright, does that make sense? Now I just want to show you this as the last question, but it said predict if a precipitate would form. Again, we haven't covered this yet. I'm not going to do it before spring break. What you would do is you'd have to find Q, and this is what I mean by how you have to deal with the change in volume. It gets nasty. You do the volume they give you times the concentration divided by the total volume. The volume they give you times the concentration divided by the total volume. And you got to solve for this Q, compare it to K, and then we'll tell you if it'll precipitate. It's cumbersome, so we're just going to skip it. Right, any other specific questions? Like this one? Okay. Alright, let me go back to this one. Yes, right here? No, because it tells you specifically. That's actually a great question, so let's go back and look at it. It tells you right here that, actually this is good. It tells you that 0.1 mole has been dissolved in 1 liter of a KF. Okay, we know potassium's gone, right? Well, because it has a subscript of 1, that the concentration is equal to the F minus. Now, let's pretend all of a sudden this was 2 liter. What would be your concentration? 0.5. Actually, not. No, be 0.05 because it's moles divided by liter. That'd be real dirty if they did that. Okay. Any other questions?